Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video we're going to talk about future value of ordinary general annuities. Before we get started with actually calculating future value of ordinary general annuities, let's talk about what is an ordinary general annuity. So first of all, any annuity is equal payments at regular intervals. And then those can be divided into two types depending on when those payments are made. If the payments are made at the end of the interval, it's called an ordinary annuity. If payments are made at the beginning of the interval, then it's called annuity due. And then for each of those, they can further be subdivided depending on the frequency of the payments and the frequency of the compounding. So each of those can be split into simple and general. And what makes an annuity simple is if the frequency of the payments is equivalent to the frequency of the compound periods. So if the payments per year is equal to the compound periods per year. On the other hand, with general, the frequencies are not equal. So the number of payments per year is not equal to the number of compound periods per year. It's the same thing with annuities due. I've already covered the formulas and calculations involved with ordinary simple annuities. I've also covered the formulas involved with simple annuities due. In this video, we're going to focus on ordinary general annuities. So that means that the payments are at the end of the interval and the frequency of the payments and the compound periods is not equal. Let's take a look. Our first example says $500 is invested into an annuity at the end of each month. If the interest is 8% compounded quarterly, what is the future value of this annuity in 10 years? So we're investing at the end of the interval, so that means it's an ordinary annuity. And we're making payments monthly, however, we're compounding quarterly. So because those frequencies are not equal, it is a general annuity. So it's an ordinary general annuity. Therefore, we can't use the formulas for ordinary simple annuities. Instead, we need to do one of two things. Either we have to change our interest rate that's compounded quarterly to an equivalent rate that's compounded monthly. So we're changing one nominal interest rate to another nominal interest rate. Once you've changed that, then you can use the formula that we used before for simple annuities. However, that's not my preference because I find that it's going to be easy to make mistakes doing the calculation and changing the interest rate and then taking that new value and plugging into a formula. Instead, what we're going to do is use one formula and just plug everything in all at once. Unfortunately, the formula looks pretty intimidating, but let's go through and talk about what each of these values represent, and then I'll show you how you can use this formula with this particular example. So future value will equal the payment amount times, a lot of series of brackets here, but at the innermost we have 1 plus I, where I represents the interest per compound period. And all of that is raised to the exponent of CY divided by PY. CY represents the number of compound periods per year. PY represents the number of payments per year. Then we raise all of that to the exponent of N, where N is the total number of payments, minus 1. And then in the denominator, we have 1 plus Y to the same exponent, CY divided by PY minus 1. It looks messy, but let's put our numbers in and try to simplify it as much as we can. So let's get this information summarized in a timeline. We're starting today and looking at 10 years in the future, and we want to know the future value when we're making $500 monthly payments at the end of the month, and those payments are earning 8% compounded quarterly. So our payment amount is $500. I will be 8% divided by the number of compound periods in a year. If it's compounded quarterly, there will be 4. We can write that as 0.02. In this case, we're able to get away from the fraction and write it as a decimal. Sometimes you'll have to leave it in fraction form if it doesn't equal a nice even decimal. N is the number of payments. So there's 12 a year, 12 payments a year, times 10 years will be 120. The number of compound periods per year is 4. And the number of payments per year, if they're monthly, there's 12. Let's plug these values into our formula. So future value will equal 500 times 1 plus 0.02 to the 4 divided by 12. then to the power of n, which is 120, minus 1. In the denominator, we'll have 1 plus 0.02 to the same exponent, 4 divided by 12, minus 1. Before I enter this into the calculator, I'm going to do some simplifications. First of all, 1 plus 0.02 is just 1.02. Then 4 divided by 12 I can reduce to 1/3. And I can do one more simplification. Going back to the laws of exponents, if I have a power raised to another exponent, I can simplify this by multiplying the exponents. So x squared raised to the power of 3 will be equal to x to the 2 times 3, or 6. I'm going to do the same thing here. If I have 1.02 to the 1/3 and then raised to the power of 120, I can simplify by multiplying those two. So 1/3 times 120 is 40. If you don't want to do the simplifications that I did first, that's fine. Just be very careful when you're entering it all into the calculator. Either way, we'll get a future value of $91,204.34. Fortunately, there's a much easier and shorter way of doing this calculation, and that is by using the Texas Instrument BA2 Plus calculator. We're going to do the exact same question, but this time we're going to use our Business Analyst calculator. The functions for time value money, which we use for annuities as well as compound interest, are these white ones. But let's get our information sorted out before we start plugging values in. So first of all, payments per year. We're making payments at the end of each month, so that means there are 12 payments per year. Our money is compounded quarterly. That means that there are 4 compound periods per year. N is the number of payments. 12 payments a year times 10 years will be 120. Interest rate is 8%. We leave it as a percent. Present value is 0. Payment of $500. We're going to enter that as a negative. That money is coming out of our pocket into the annuity, and we want to calculate future value. Anytime you're using these functions, you want to make sure that any previous work is cleared before you start. In order to do that, if you look above the future value function, it says clear TVM, time value money. So let's go second function, future value, and that will clear anything you've done before. Then we want to start by putting the P per Y and C per Y. P per Y is above the I per Y, so the number of payments per year. We go second function, I per Y, and we get P per Y. We want that number to be 12, so we enter 12, 12, enter. When you scroll, you'll see that compound periods per year automatically change to the same value. We don't want 12, we want 4, so let's enter 4. Now we can quit by going second, quit. To enter these values, put the number in and then the function. So N is 120, so we put 120 and then N. Interest per year is 8. For present value, we can put a 0 if we want, but because we've cleared the work we did before, it'll automatically be 0. Payment is negative 500, so 500, make it negative, payment. Now what we want to do is calculate future value, so compute future value, and we get $91,204.34. This is the same value we obtained when we used the formula. However, this is much quicker and much easier. Our second example is a little bit different because we're starting with money already in the account. So it says a savings annuity already contains $15,000. If an additional $300 is invested at the end of every month at 6% compounded semi-annually for a term of 20 years, what will be the maturity value of the investment? I wrote a little timeline. We have a present value in that account of $15,000. Both that and the annuity is earning interest at 6% compounded semi-annually. We're making monthly payments at the end of the month of $300. We want to find the future value. So this consists of two things that are growing, this $15,000 that's sitting in the account, as well as the annuity. So what we're going to do here is we're going to treat them separately. We need to find what the future value will be of this $15,000 investment. We're just simply going to use our compound interest formula for that. And then we're going to calculate the future value of these payments in 20 years. So let's start with finding the future value of $15,000. So future value using our compound interest formula will equal our principal, or our present value, which is $15,000, times 1 plus I. Now, I, in this case, is their annual interest rate divided by the number of compound periods in a year, which is 2. So I will be 0.03. And we raise that to the number of compound periods in total in 20 years. If it's compounded semi-annually, there's 2 a year, and we multiply by 20 years. So to calculate that, we're going to take 15,000 and multiply by 1.03 to the exponent of 40. And that $15,000 will have a future value of $48,930.57. Now let's find the future value of this annuity. Let's define all of our values that we know, and then we can plug into our formula. Our payment amount is $300. The interest per compound period is 0.06 divided by 2, which is 0.03. The number of payments will be 12 payments a year times 20 years will be 240. The number of compound periods per year is 2 because it's compounded semi-annually, and the number of payments per year is 12 because it's monthly payments. When I plug these values into the formula, I get future value equals 300 times 1 plus I added 0.03 to 1 and got 1.03, to cy over py, which would be 2 over 12, to the power of n, which is 240, minus 1, over 1 plus I is 1.03, to the same exponent, 2 over 12, minus 1. Again, I would simplify this before I started punching this into my calculator. So this simplifies to 1/6. So does this. Then I would use my law of exponents that would allow me to simplify this and get 1/6 times 240, which is just 40. When I do the calculation, I get $137,409.04. So that's going to be the future value of this annuity. Now let's find the total future value or the maturity value of the investment by adding the future value of the $15,000 as well as the future value of the annuity. When we add these two values, we get a total future value or a maturity value of $186,339.61. Well, let's try this question again, but using our calculator to do the work for us. Let's start by finding all of these values and then entering them into our calculator. So the number of payments per year is 12 because it's payments every month. The number of compound periods per year, if it's semi-annually, is 2. N is the number of payments. So there's 12 payments per year times 20 years will be 240. Interest rate per year is 6. In this question, we have a present value of 15,000. So we're going to enter that, and we need to make it negative. You can think of that money going from your pocket into an account, so it's negative. Similarly, the payment will be negative. It's negative 300. And we want to calculate future value. Before we start, I'm going to clear any previous work. So second function FV is the clear. And we're going to start with payments per year and compound periods per year. So I go second function I per Y. Payments per year is 12. We're good with that. Scroll. Compound periods per year is 2. We're good with that. So we're going to quit. Now we're going to enter these values. 240 is N. 6 is I per Y. Negative 15,000, so 15,000, make it negative, is present value. Payment is negative 300. And we want to compute future value, so compute future value. And we get a future value of $186,339.61. As you can see, using your calculator functions for time value money, it's much easier than actually doing it through the formula. But you've got both options, and if you're not making any mistakes, your results should be the same. In my next video, I'm going to talk about present value of an ordinary general annuity. See you then.